Assalamu alaikum dear students, welcome back to my channel. In today's lecture we are going to talk about some basic terms that are extensively used in group theory. So we are going to start with the definition of complex numbers. Complex numbers are very important in different areas of group theory. For example, we have a group that we call as a group of nth roots of unity, which is a group under the operation of multiplication. We will see that later, but it was necessary to talk about it so that you can understand the importance of complex numbers. Anyhow, the definition of complex number is quite simple. You people are already aware of this in different subjects like complex analysis or calculus or many other areas of mathematics use this entity. So it's quite obvious, it's very easy to understand. Now the complex numbers are numbers of the form a plus b iota, where a, b are real numbers and this iota is equal to square root of -1. Okay, so all the numbers like 2 plus 3 iota, -7, -4 iota, or even let's say -9 iota or even 3, all of these are complex numbers. Okay, if you talk about this one, you might be wondering it should be of the form a plus b iota. Why is it just -9 iota? It's very easy. You can just add 0 here and this will be of the form a plus b iota. Similarly, over here you can write 3 plus 0 iota, so this will also be of the form a plus b iota. Alright, ladies and gentlemen, next is a technique that we will use extensively in proving many results in group theory, and that is known as mathematical induction. By the way, this is not limited to group theory. You use this method in many other branches of mathematics as well to prove some statement for some integers. So this technique is known as mathematical induction, as it is clear from the name that it is an inductive method. So how do we do that? Mathematical induction is a technique to prove that a given statement holds for n equal to 0, 1, 2, 3 up to so on. This technique consists of two steps. In first step, we prove the given statement for the base case, that is n equal to 0. In second step, we assume that statement is true for k belongs to integer, I mean any positive integer, and then prove it as if it holds for k plus 1th integer as well. Okay, so this is how it works. I'm not going to explain it too much because you have already used this in your A-level, O-level mathematics, so I think we should move on. And now we are going to talk about the very elementary concept of Cartesian product of sets. So let us say you have two sets A and the set B, and they are non-empty sets. Then their Cartesian product, which is denoted by A cross B simply, is defined as, now this product consists of order pairs. Now this will be a set of order pairs where the first element, I mean A, will be from the first set A, and the second element B, this will be from the set B. Okay, so here I have an example for you people. So if you have a set which contains two elements 1 and 2, the other is B set which contains 3 and 4. If you take their Cartesian product, you will get this result, and here you can see the definition is being satisfied. In every order pair, the first element is from the set A and the second element is from set B. Also keep this in your mind that in general, A cross B is not equal to B cross A. Alright, ladies and gentlemen, let us define what a relation means. Now a relation R, we usually denote it by R, but this is not necessary. You can name it by any alphabet. So a relation R from a set A to B is a subset, this word is important here, of the Cartesian product of A and B. In our last page, we have talked about the Cartesian product. Now if you find the Cartesian product of A and B, you will get a set of order pairs, and if you take sum of them in a new set, you form a new set which consists sum of those order pairs that might be equal to the that might consist of all the order pairs as well, just like an improper subset. So that new set will be called a relation from this set A to set B. Okay, so here I have an example for you. We have used the same Cartesian product A cross B. So A cross B was consisting of 4 order pairs, and I have taken out of them 2 out of them. So this set over here is actually a relation. Okay, also I have another relation over here So the things get clear here that there does not exist a single relation for a Cartesian product. There might be many of them, and precisely speaking, how many of them? So the number of possible relations from a set A to a set B is 2 to the power the product of cardinality of A and B. Okay, so this is the formula by which we can find how many possible relations exist. So if we talk about this Cartesian product, these two sets, then the relations that can be formed between these two sets is equal to 2 to the power the cardinality of A. As you can see on our previous page, the cardinality of A was 2, so it will be 2 cross, and the cardinality of B was 2 as well. So this is 2 to the power 4, which is equal to 16. So there are 16 possible relations that can be formed out of the Cartesian product of A and B. And now we are going to talk about domain and range of relation. Now if you have a relation, okay, you know very well that a relation consists of order pairs, okay, that are taken from the Cartesian product. Okay, now if you take the set of first elements of each order pair, okay, that will give you the domain of the relation R. Similarly, if you take the second elements of the order pairs, each order pair, then you will get the range of relation. Okay, here I have an example for you, and this time we are using a relation which consists of 3 order pairs. Okay, and if I take first elements of these 3 order pairs, those are 1 and 2. Now keep this in your mind. Actually there are we have 2 elements. This 2 over here and here is actually repeating, but you are not going to use it twice. You will write it only once, as we do with the sets. Okay, similarly the range over here is consisting of 3 elements. Number 1 is 2, number 2 is 3, number 3 is 4. Now these 3 elements are in the range of relation because these are the second elements of each order pair of the relation that we are talking about. And now, ladies and gentlemen, let us explore the concept of relation further. Let's go deep down, and now we are going to talk about the types of relations. Okay, so let's say we have a set A and we are going to define a relation on A. By the way, when we say we are defining a relation on A, that means the relation is being defined, or you can say the subset R is being formed from the Cartesian product of A with itself. Okay, so it should be clear in your mind because we will use this extensively in our study. So keep this in your mind. Whenever we say R on A, relation on A, that means the relation is now a subset of the Cartesian product of A with itself. Okay, so let's say we have a relation R on the set A. So there are 3 or 4 types that we usually talk about, and that you can easily find in any book of set theory. The first one is reflexive. Okay, the relation is said to be reflexive if such pairs belong to R for all A belongs to A. For every element of the set A, the order pair AA should belong to R. Okay, if it happens, then that relation will be called reflexive relation. Okay, the next one is symmetric. Now here we say that if for all AB belong to R, we have BA belong to R, then R is said to be a symmetric relation. Now what does it mean? It means that if A is related to B, B should be in small letters. If A is related to B under R, then B should also be related to A under the same relation R. Okay, this is what it means. And the next one is anti-symmetric. Okay, so here we say that if whenever AB and BA, both of these belong to R, then A and B should be equal. Okay, only this should happen only when A and B are equal, then we call that relation to be anti-symmetric. Okay, and the next one is very important type of the relation, and that is the transitive relation. So it says that if you have AB and BC, these 2 order pairs in R, then you should have a pair where A and C should be directly related through R. Okay, then that relation is called the transitive relation. And now we have another type of relation which is actually combination of these 3 types of relations. Now if a relation is reflexive, symmetric and transitive, such a relation is called an equivalence relation. Okay. Alright, let us now talk about the equivalence classes and their properties. Let me tell you people that this concept is very important, especially when we will study the conjugacy classes and conjugacy relations and so on. This will be very important there. So what does it mean to be an equivalence class? Okay, we say that let E be an equivalence relation on a set A. For all x belong to A, let this denote the set like this. Then this set is called the equivalence class of X, the equivalence class with respect to E determined by X, I should say. Now what does it mean? Let me explain this. You have an equivalence relation E on the set A. Okay, if it is equivalence, then it means it is reflexive, it is symmetric, and it is a transitive relation. And we are defining a set which contains all those elements of the set A which are related to this element X by the relation E. Okay, this set is called equivalence class with respect to E determined by X. Okay, if three elements are related to X, then those set of those three elements will be called the equivalence class with respect to E determined by X. Okay, and here are some properties for the equivalence classes, and these properties are very important, very simple, and very interesting, I should say. The first one is that let E be an equivalence relation on A, then for all x belong to A, this set will not be empty set ever. How? Because we have already said that E is an equivalence relation. Now if E is an equivalence relation, then it means that for all x belong to A, the pair XX will surely be in the relation. Okay, and that means if X is not related to any other element of A, still it will be related to itself. So it will never ever be an empty set. The second property is that if Y belongs to the conjugacy class of element X, then their conjugacy classes will be same. Okay, so you can simply verify this using the symmetric and the transitive property of equivalence relation. Okay, the third one over here is for all xy belongs to A, either they are identical or they will be disjoint. Okay, so the fourth property over here is the set of all equivalence classes. If we take their union, that will give us the whole set A. Okay, now let us go through the concept of the partition. Now the partition is defined as let A be a set and lambda be a collection of non-empty subsets of this set A. Then lambda is called a partition of the set A if following properties are satisfied. The first one is that since it is a collection of sets of subsets of A, so if you take any two of them, then either those two subsets will be identical or their intersection will be phi, or you can say they will be disjoint. Okay, the second property is this: if we take union of all those non-empty subsets which are present in this class, their union will be the whole set A. Okay, and here I have an example for you. The set A is consisting of 5 elements, 1 2 3 4 5. Here we have a class of subsets which consists 3 sets. The first one contains 1 2 element, the second one contains the singleton element 3, the third one contains 4 5. It's very clear, if you take the intersection of any two of these, you will get phi. So the first condition is satisfied. The second condition, which says that their union should be the whole set A, if you take union of these 3 sets, you will get A. So this class of subsets, the lambda, is a partition of this set A. Okay, now the interesting thing that is necessary to mention here is that what we have defined in our last page, I mean the equivalence classes, they also defines the partition of that set A. Okay, using the relation, let's say we called that relation E in our previous page, so I'm mentioning it over here. So equivalence classes actually defines a partition. We will talk about this in detail when we will be discussing the topic of conjugacy classes, and that will be quite interesting there.